Alright, welcome to the next episode of processing waveforms outside of the picoscope. Today we are going to process a waveform collected by Justin Miller for Diag.net. It is a 2.5-liter Toyota engine, and along with CKP and CMP waveforms, we also have the in-cylinder pressure transducer waveform along with the ignition trigger for it. We are going to save this file into text format and load it in Octave. We are going to use exactly the same technology as in the last video to uncover the angular position and speed. So let's jump right into the results. Let's plot all the traces along with the speed of the crankshaft. This is what we are going to see. We see that the crankshaft speed is changing over time and uncover the TDCs for all the cylinders. To confirm that the angular positions are correct, let's add the phase rulers. I'm using not a particularly optimized algorithm for that, so it will take a while. But we can already start looking at what happens when the cylinder is approaching the TDC. First, the compression event happens, so the crankshaft speed is getting slower, but then the combustion event happens, and then the speed of the crankshaft is increased drastically. This happens for 3 out of 4 cylinders. For the cylinder in which the transducer is in, the compression event happens as normal, but it is not followed by the combustion event, so the speed of the crankshaft continues to go down. Now that we are sure that our angular positions are correct, they do align with the TDCs, let's try to plot the data in a different way. Here we have the x-axis being the time in seconds. But what would happen if we used the angle from 0 to 720 degrees as our x-axis? Let's plot just that. And this is quite a fun picture here that tells you exactly what's happening for each angle of the crankshaft. Now, this is just one revolution of the engine. Let's try to overlay this with the next 720 degrees of rotation. So we just slapped on another picture like that for the next revolution, and what do we see? We see that all the CKP, CMP, pressure, and ignition triggers match exactly. The speed, however, changes just a little bit. What we see is repeatability in our waveforms, which is what we want from a normally operating engine. If we go ahead and add another revolution, we will only confirm our hypothesis that everything that's happening in the engine is pretty much repeatable. The speed does change a little bit, which is no big deal. This is not the only way to present an angular plot. In mathematics, the polar plots are often used. So we are going to go ahead and issue commands to plot the polar plot and see how it looks like. And this is quite fun. It's pretty much the same information as before. It does confirm that we have repeatability in our signals, and note that the speed over here would be a perfect 4-leaf clover if there was no pressure transducer for this cylinder, because then there would be even peaks and valleys in this plot. However, here we have a pressure transducer for that cylinder, so it does not contribute because there is no combustion event happening, and that's why we have asymmetry in it. Overall, I think it's just a fun plot. Most diagnosticians would prefer the plot that we had previously. Okay, let's move on and ask ourselves the following question. This polar plot is for 0 to 360 degree of camshaft rotation, or equivalently 0 to 720 degrees of crankshaft rotation. However, each crankshaft position corresponds to a certain volume in the cylinder. So can we use that information to plot the volume in the cylinder versus the pressure? How would this plot look like? And would it be similar or dissimilar to the plots that we find in textbooks for, let's say, a steam engine or for a 4-stroke engine? To do that, we would need to look up the engine parameters such as the piston stroke, displacement, and also implement the slider crank model that will identify the piston position, from which we can then calculate the volume in the cylinder. So let's do just that. So here I define the necessary values and functions, and then I can identify the volume in the cylinder. When I plot those values, I get this interesting graph. It's all revolutions of the engines plotted at once, and they perfectly overlay one each other, confirming that there is repeatability in our pressure waveform. However, we cannot really see from this graph which strokes the engine is in. So let's do some coloring and get a pretty plot where we will see where each stroke is. And now this is pretty beautiful. We can see the compression events happening, but at first the intake valve is still open, so the pressure stays constant. Once the intake valve closes, the pressure starts to rise rapidly until the cylinder hits the TDC. There is no combustion event happening because we only have air in the cylinder, so there is no pressure spike like we've seen for the typical 4-stroke engine cycle in the textbook. Instead, there is an expansion stroke here happening. We just slide down all the way down until the exhaust valve opens and exposes the cylinder to the atmospheric pressure. We go back to the TDC where the exhaust valve closes, the intake valve opens, and we are going back with the volume increasing while the pressure stays at the pressure of the intake manifold. Very pretty graph. Alright, before we go, here is a thought-provoking question to the viewers. We have the compression event that has this following shape, and the question is it just a reciprocal function, 1 over x, or something more complicated? And what would it mean for the compression process if it were a reciprocal function? Alright, thank you for watching, and please let me know your thoughts and comments in the box below.